Today we will talk about existence and uniqueness of solutions to initial value problems. So in class, I asked you to look at two differential equations. The first being dy dt equals 2y squared with an initial condition that y of 0 equals 1 over k. And what we noticed is that the solution to this differential equation only exists for times between 0 and k over 2. So the solution doesn't exist for all time. It only exists for that smaller interval. The second differential equation that we looked at was dy dt equals 3/2 y to the 1/3 and y of 0 equals 0. And in this case, we were able to show that y of t equals t to the 3/2 is a solution to that problem, but also that y of t equals 0 is a solution to that problem. In fact, I defined a whole family of solutions to that problem. So even though there was only one initial condition for this problem, I was able to find infinitely many solutions that corresponded to that one initial condition. And so in each of these cases, we have an issue with the solution to our differential equation. In the first case, the solution did not exist for some times. In the second case, there was a solution, but that solution was not unique. There were lots of different solutions. So the issue came about because both of these examples are nonlinear differential equations. And with dealing with nonlinear differential equations, we have to ask the questions, does the solution exist? And is that solution going to be unique? So something of concern when looking at an initial value problem is, can we look at that problem and immediately be able to ask the question whether there's going to be a solution and whether that solution is going to be unique? This is important because if you're trying to model a physical system, you want to be able to take those assumptions, turn them into a differential equation with an initial condition, and then be able to say that you can solve that differential equation to find out what the solution is to describe the physical phenomena. Okay, so let's talk about a general ordinary differential equation. In this case, dy dt equals f of ty. So what does it mean for y to be a solution? So I'm going to let y be some function. We'll call it phi of t. Now, I'm going to write y as this function phi of t because I'm thinking about y as being the solution and phi of t as being the formula for the solution. Okay, so what does it mean for y equals phi of t to be a solution to the differential equation? Well, what it means is I should be able to take the derivative of phi. I should be able to take that derivative of that formula, and then when I substitute the formula into the right-hand side and I do f of t, phi of t, then that equality should hold. Okay, so that's what it means to have a solution to the differential equation. The question is, can there be more than one solution? So if phi of t is a solution, can there be more than one? Well, yes, we've seen this in the past. We've seen that dy dt, if it equals, say, a times y, well then y of t as a solution has the form c equal to the c e to the at. And that c is an arbitrary constant. And so we can see that there can be more than one solution to the problem. In this case, there are actually infinitely many solutions. Each one of those solutions, though, corresponds to an initial condition. So once I specify the initial condition, then I can specify what the constant C is. So then when you're given that initial condition, what does it mean for a solution to be unique? Okay, so what I want to know is whether when given one initial condition, will the solution be unique? Will it be the only solution? Okay, so what it means for a solution to be unique is if we let phi prime of t equal f of t phi of t. So if we let that formula be a solution to the differential equation, and we say that phi of 0 is equal to y sub 0, so it satisfies the initial condition, then if we find another function, we'll call it psi of t, so that if I take the derivative of psi of t, then it's f of t psi of t. If that is true, and psi of 0 equals psi y sub 0, so if I find another solution out there that satisfies both the differential equation and the initial condition, if the solution is unique, then it must be that psi of t and phi of t are equal for all time. So for a solution to be unique, what we're saying is that if we find two different solutions to the initial value problem, then those two solutions, if the solution is unique, must be equal. Okay, so that now that we have an understanding of what uniqueness is, this is going to bring us to what's called the existence and uniqueness theorem. Okay. So the theorem says, let the functions f of t, y, and df, dy be continuous in some rectangle. Okay, so let me specify for you what this rectangle is going to be. So we're going to look at t being between a and b. And we're going to look at y being between c and d. And what we're going to say is if you look at this region of the plane, we're going to say that both the right-hand side of the equation, f of ty, and the derivative of the right-hand side are both going to be continuous within that rectangle. And we're going to say that that rectangle contains our initial point. So in this case, our initial point is going to be t0, y0. Okay, so we have the right-hand side and the derivative of the right-hand side with respect to y are continuous in the rectangle. That rectangle contains our initial point. If these things are true, then in some interval, t sub 0 minus h less than t sub 0 plus h contained within the interval between a and b. So in some interval, so I'm going to define a little interval here, t sub 0 minus h to t sub 0 plus h. Within that interval, there exists a unique solution to that initial value problem. dy dt equals f of ty, and y of t sub 0 equals y sub 0. Okay, so what does that mean? Okay, I have my right-hand side is continuous. The derivative of the right-hand side with respect to y is continuous within the rectangle. What that tells me is for a short amount of time, I can guarantee that there exists a solution to the differential equation. I've drawn that there in blue. And not only does there exist a solution, but that solution is also unique. Now, we should point out that the solution exists for a short time interval. Okay? I didn't say that the solution was going to exist for all time. I just said it was going to exist for short time. And you might see that as being a drawback and saying, okay, well, I only know that the solution exists for a short time. How is that helpful? Well, once you know the solution exists for a short time, you can then make a new initial condition, maybe that initial condition right here, and then you can say, oh, well, from that initial condition, I have f of ty and df dy are both continuous, and so the solution must exist for a little bit longer. Okay, and I'm still within the rectangle, so then my solution must exist for a little bit longer, and I can keep playing that game at least till I get to the edge of the rectangle. And so the solution will exist at least within the entire rectangle, where I can say that my right-hand side is continuous and the derivative with respect to the right-hand side is continuous. Okay, so that's the conclusion to this theorem. It's only for a short interval, but we can use the conclusion to extend the solution for a little bit larger interval. The second thing that you have is there not only exists a solution, but there exists a unique solution. Okay? So what does that mean? That means if two solutions start at the same initial value, they must be equal. So what that means is if I was to try to start another solution here, let's say that I was able to find another solution, like I actually shouldn't be able to find another solution there, because no solution should be able to cross that initial value. Okay, so what I've drawn in red cannot happen. I cannot have two solutions that cross, because if two solutions crossed, that would mean that if I started at that initial value where the two solutions crossed, then they should be equal going forward from there. Okay, the two solutions that meet at that starting value would have to be equal. So essentially, uniqueness tells us that solutions cannot cross. Okay, so in this case, we can say solutions cannot cross each other. And that is an important result of the existence and uniqueness theorem. Now, I'm going to present this theorem without proof. And that is because in order to understand the proof of this theorem, you need to take a class in what's called real analysis, which is a very in-depth study of the concepts of calculus. And you need that language of the class real analysis. You need the language that you learn in that class to be able to construct a proof of the existence and uniqueness theorem. So I'm going to ask that you take it on faith that this proof exists and that this theorem is valid. I will say some other things about this theorem, and that is we can actually guarantee just existence but not uniqueness if the right-hand side is continuous. So as long as the right-hand side is continuous, then we can guarantee existence. Okay? In fact, we can tell you exactly what the solution is going to be. We've talked about this before. Y of t is actually y0 plus the integral from t0 to t of f of s y of s ds. I can actually write down what the formula is, even though it might be difficult to compute that integral. That is the solution. So as long as f is continuous, then I can write down what the solution is. But I need the derivative of the right-hand side with respect to y to be continuous in order to get uniqueness. That's important. If you go back to the example that we looked at before, you'll notice, okay, that this differential equation, dy dt equals y to the 1/3, 3/2 y to the 1/3. You'll notice that the right-hand side is continuous, but in this case, with df dy, when we take the derivative, we're going to get 1/2 y to the minus 2/3, and you notice that that is not continuous when y equals 0. And in fact, for this example, it was when y equals 0 that we saw that solutions intersected. Okay, so this particular differential equation did not satisfy the uniqueness part of the existence and uniqueness theorem. Okay, it did not have the derivative not be continuous in the rectangle. So because the derivative was not continuous at y equals 0, then we saw uniqueness problems when y equaled 0.